Hey, so following on from the last one about inductors itself, just now to talk about how they behave in DC circuits. But before going to that, I just want to go quickly back over capacitors in DC just to make sure it's a useful comparison. So just a quick review, if we have a two-way switch to discharging circuit, some concepts with capacitors, if we have the capacitor voltage as charge over capacitance, that means we can talk about the capacitor voltage being proportional to charge. The more charge there is on the capacitor, the more voltage there is on the capacitor. If we want to talk about resistor voltage, we can use Ohm's law to relate that, where voltage across the resistor is proportional to current. So the more charge on the capacitor, the more capacitor voltage is, the more current there is, the more resistor voltage there is. So if we charge a capacitor, so we close it to the connection A on the circuit, and we get charge building up on the capacitor. So as charge is building up, we have, in the relationship we're just talking about, that means we're going to get more voltage across the capacitor. Okay, so if we would plot a graph of capacitor voltage over time, we get an increasing trend like this. It plateaus as the charge plateaus as we get to when it's fully charged, and that will plateau off at the supply voltage. It will tend towards the supply voltage. Because in the loop we've got a supply voltage, a resistor and capacitor, we can apply Kirchhoff's voltage rule, and the supply voltage must be equal to the capacitor voltage plus the resistor voltage. And because we already know the capacitor voltage is increasing and the supply voltage is constant, that must mean the resistor voltage therefore decreases. So if we plot resistor voltage, it's going to start at the supply voltage, seeing as the capacitor voltage starts at 0, and it's going to decrease. Okay. Now, as charge is building up on the capacitor, like for example on the negative plate, the more electrons are put on that plate, the harder it gets to push more electrons on, because the electrons already on the plate are repelling further electrons. So it gets harder and harder to push current around that circuit onto the capacitor, so that reduces the current. Or another way of thinking about it, due to Ohm's law, if we know the resistor voltage is decreasing, which we do, and the resistance is constant, the current must also be decreasing, which means if we plot current, it's going to start off at an initial current of Vs over R, and it's going to drop away. So the resistor voltage and current look the same, and that's the true for any electrical circuit. Resistor voltage and current are always in phase. They always have the same shape graph. Okay. Now, if we flick the switch over to the other side then, okay, we've got a charged up capacitor, and we flick it over and we're now discharging it. So as charge leaves the capacitor, now if we apply the same logic as before, as charge is leaving, that means the capacitor voltage must also be decreasing, okay, because it's less charge. So it's going to start off, if we assume it was fully charged to Vs initially, it's going to start at Vs and it's going to decrease as the charge leaves. And now Kirchhoff's voltage rule looks a bit different now. The supply voltage, the battery, or whatever the power supply was, is no longer in that circuit. We now just have the resistor and capacitor. The capacitor is acting as the power supply and is powering the resistor. And there's only those two things in the circuit, so they must have the same voltage. And as the capacitor voltage is decreasing, the resistor voltage must be doing exactly the same thing. And if we think about current, the charge initially, you'll have a lot of negative charge on that plate. So when you connect it around to the positive plate, it will be being repelled quickly and by the other negative charges, and also attracted strongly by the positive charges on the other plate around through the circuit. So it will leave quickly, but as that amount of charge decreases, that effect will reduce, so the current will reduce. Or alternatively, if we think about it in terms of Ohm's law, we know the resistor voltage is decreasing and the resistance is constant, so the current must also be decreasing. So we get a graph like that. Now we measure how long that takes by using this quantity called the time constant, which is the time it takes for the quantity that we're dealing with to change by 63%. So that's either to increase to 63% of its total or to decrease to 37% of its total. So it's changed by 63%. And you can apply that to any of those values. For a capacitor charging circuit like this one, the time constant is RC, which is resistance multiplied by capacitance. We can assume that the capacitor is fully, well, at least fully meaning more than 99% charged or discharged after 5 time constants. In theory, it's never fully charged. It's always getting closer and closer, but never quite there, according to the theory. But after 5 time constants, it's changing so little it doesn't really matter anymore. If we're doing calculations with this, it can be easier to calculate, like for example, if you had to calculate the capacitor voltage when you're charging. The ones like graphs like this that are increasing are kind of fiddly to calculate if you're going for more than 1 time constant. So for example, if it's 1 time constant, the capacitor voltage will go up to 63% of the total. The resistor voltage will go down to 37%. That's pretty straightforward. But if it's 2 or 3 time constants, then for the capacitor voltage, you'd have to calculate 63% of it for the first time constant, and then 63% of what's left and add that on, and then 63% of what's left and add that on. They can get quite fiddly and annoying. But the resistor voltage or current, all the ones that decrease, are quite easy because you just keep multiplying it by 0.37. After 1 time constant, multiply by 0.37. After 2, multiply by 0.37. After 3, multiply by 0.37. Okay, so you just multiply by 0.37 to the power of how many time constants it's been. So if I was calculating capacitor voltage for a charging capacitor, I would actually calculate the resistor voltage and then subtract that from the supply voltage. That's, I think, the easier way to find it. And just to note that the fundamental behaviour of a capacitor is based on the attraction and repulsion of charge on the plates. That's ultimately what it's all based on. Okay, so that's like a real quick summary of capacitors. And now I just want to use that because we're going to be comparing some of those to inductors, because inductors in a lot of ways behave in the opposite way to capacitors. Based on completely different physics, but the behaviour ends up being kind of like the opposite of a capacitor. So if we have inductors in a DC circuit, so we're going to be looking at the circuit. We've got a power supply, a switch, an ideal inductor, L, and a resistor, R. Now, just to note that ideal inductors have inductance but no resistance. But in reality, real inductors have both inductance and resistance. An inductor, remember, is a coil of wire. So, and wire has resistance. It might only be small resistance, but it is there. And if you have, like, for a really large inductor, you tend to have a very long piece of very thin wire, which could have a measurable resistance, okay? But usually we end up just assuming it's an ideal inductor. Sometimes you can actually treat the resistance of an inductor as almost like the internal resistance of a power supply. Now, for inductors, for capacitors, the fundamental principle was charges attracting and repelling. For inductors, the fundamental behavior is Lenz's law, opposing changes in flux, okay? And also, I should say, Faraday's law, that the induced EMF is based on rate of change of flux. So remember, flux is proportional to current. So an inductor opposes change in flux. So you can think of that as opposing changes in current, because when you change the flux, you change the current, you're changing the flux. In a circuit like this. If we look at Faraday's law, the EMF that's induced is the inductor voltage. The reason there is a voltage across an inductor is because it is inducing a back EMF. Okay, and that happens when there is a change in current. So when the current changes, the changing flux induces a back EMF, and that opposes whatever change that was that happened. Okay. Now, when the switch is closed, now, a note about terminology here. Don't use the terms charging and discharging for inductors. Charging and discharging are used for capacitors because they store and release charge. Inductors do not store or release charge, so you can't really use those terms, although it's kind of, almost a reflex to use it sometimes. Okay, it's not really an agreed term on it. Like the terms increasing current and decreasing current are just commonly used for when you close the switch, the current increases. When you open it, the current decreases. I'm going to use the term fluxing and defluxing. I like them, but they're not official terms. Okay, so when you close a switch, current starts to flow, so the flux through the coil increases. I call that fluxing. When you open a switch, the current through the coil decreases, so the flux decreases. I call that disfluxing. But those are not sort of officially recognized or proper terms. It's just a term that I use. So I'm going to call this fluxing, okay? So the inductor voltage over time, what will that look like? So initially, we get a large rate of change of current, but it's limited by a large opposing back EMF, because if the rate of change of current is large, the back EMF is large. But there's a limit to how big it can be in this situation because of Kirchhoff's voltage rule. Okay, we've got three components in that circuit: the supply voltage, the power supply, the inductor, and the resistor. So the supply voltage must be equal to the inductor plus resistor. Okay, so the maximum value that the inductor voltage can be is the supply voltage. And that will be what the initial one is. The initial value of the supply, of the inductor voltage, will be equal to the supply. But over time, as the current increases, it's going to tend towards a steady state. It's going to plateau off. So because it's changing less, the delta I over delta T is decreasing. So the induced back EMF will decrease. So the inductor voltage will look something like this. Okay, it will start off at the supply voltage and drops away. Okay, and eventually the current will reach a pretty much constant state. So the rate of change of current tends to zero. So the back EMF also tends to zero. Now, if we think about what the resistor voltage would look like, because we know we've got Kirchhoff's voltage rule there, we know the supply voltage is constant, and we know the inductor voltage is decreasing because the rate of change of current is decreasing. That must mean the resistor voltage is increasing. So it's going to start at zero, and it's going to increase, and it's going to head towards a value of the supply voltage after a long period of time. And current, well, two ways of thinking about it. One is like just thinking about what we talked about before, but the other one is just looking at Ohm's law. We know the resistor voltage is increasing, and we know that the resistance is constant. So that must mean the current must also be increasing. So it will do the same thing as the resistor voltage, and that's, like I said before, always the case. So it will start at zero and head towards a maximum value of Vs over R. Notice that those graphs are like the opposite of what you get for charging a capacitor. Okay, so charging a capacitor, the capacitor starts at zero and goes up, and the resistor and the resistor voltage and the current both drop down. For an inductor, the inductor voltage starts high and drops down, and the resistor voltage and current both start at zero and go up. Now we quantify the time that this takes in the same way that we would for a capacitor. We use the same idea of a time constant, which is the time taken for it to change by 63%, the same as we do for capacitors. And it can be applied to any of those three things, okay? So for an inductor resistor circuit, the time constant is given by L over R. The inductance in henries divided by the resistance in ohms. That gives you the time constant in seconds. And the same as for capacitors. It's, if you're dealing with more than one time constant, it's easier to calculate the inductor voltage first because that one's decreasing. You can just multiply it by 0.37 however many times you need to, and then use Kirchhoff's and Ohm's laws to figure out the resistor voltage and current. Okay, if you're dealing with more than one time constant. So for an example, let's say we've got this circuit here with a 3.4 volt power supply, 6.8 Henry inductor, and a 17 ohm resistor. and the switch is closed at time is 0 seconds. And let's start off with one calculate the time constant of the circuit. So if we I'll just change the color. Let's say we want to, number one, we want to calculate the time constant. And the time constant for a circuit like this is L over R. In this case, we've got 6.8 divided by 17. And that's 0.40 seconds to two significant figures. Okay. So that's pretty straightforward. Plug in the numbers from the circuit. Notice that the supply voltage doesn't matter, doesn't affect it. All right, what's the potential difference across the resistor after 1 minute? So first of all, 1 minute now is 60 seconds. Now in these circuits, it's not so much how many seconds it is, it's how many time constants it is that really matters. 60 divided by 0.4 is 150 time constants. Okay, now that's a lot of time constants. Remember, it's basically constant after about 5. It's reached pretty much a steady state. So we can assume this has reached a steady state. Okay. Now, if nothing's changing, the inductor voltage is going to be 0. Okay. There's nothing changing. There's no change in current anymore. Okay. That means the resistor voltage is going to be equal to the supply voltage. Because the supply voltage all has to be used somewhere. It's 3.4 volts. Okay. After 1 minute. Okay. Number 3. What is the current after 1.2 seconds? So first of all, 1.2 seconds divided by 0.4. So 1.2 seconds divided by 0.4 seconds is 3 time constants. Okay. Now this is one of those ones where it's going to be, if we just first of all look at, if we did a sketch graph, it looks like it's not a very straight line. This is current against time. It would look something like that. Okay. Where it'd be heading towards some maximum value. But this would be one of those really annoying ones where we'd have to go one time constant, then figure out that it'd be 63% of the total, then figure out the second time constant, and then figure out the third one, and it'd just get quite messy. Okay, I'm not going to do it that way. Okay, what I'm going to do instead is I'm going to calculate what the inductor voltage is, because the inductor voltage drops down. Okay. So I'm going to calculate what the inductor voltage is, and then I'm going to use that to find out what the resistor voltage is, and I'm going to use that to find the current. Okay, that's how I'm going to go through this. So, first of all, the inductor voltage after 3 time constants is going to be the supply voltage, 3.4, and it's going to be, now after 1 time constant, it's going to be 37%. After 2 time constants, it's going to be 37% of that. After 3 time constants, it's going to be 37% of that. Okay, which I can write as 3.4 times 0.37 cubed. Let me just get my calculator. 0.37 cubed is 0.17 volts. That's the inductor voltage at that time. Okay. The resistor voltage at that time, well, we know that supply voltage is shared between the inductor and the resistor, and we know how much the inductor is using, so it's going to be, sorry, pen there for a second. The resistor voltage is going to be supply voltage minus the inductor voltage. So it's 3.4 minus 0.17 is 3.23 volts. And then to find the current, I'm just going to use Ohm's law. I know the resistor voltage and I know the resistance. So it's 3.23 divided by 17 is 0.19 amps. Okay. So that's how I would go through some calculations like that. That's just some simple calculations, sort of calculations you might come across. Okay, so that's all for like closing a switch. Now, what about opening a switch? Now, first of all, how long does it take to open a switch? Your gut reaction might be, well, it's instantaneous, but it's not actually instantaneous. Now, this video, this is a 500,000 volt switch. So this is an extreme example, but what happens when the switch is opened? Okay, so you see how in there you got an arc for me there. Oh. So it's a short amount of time, but it's not zero. Okay, it doesn't take long for a switch to open, but it's not at 0 seconds. Now, this is, for a 500,000 volt switch, that was a few seconds that took. But for any switch, you get an effect like that. You get arcing between the switch contacts. So for a normal switch, delta T is very small. Okay, so that means your rate of change of current is very large. It goes from whatever current it starts at to 0 very quickly. So delta over delta T is very big, which means you get a large induced back EMF. Okay, that leads to some slightly different behavior when you open a switch. Okay, so if we have our same circuit and the switch has been closed for a while, it's reached a steady state. But when you then open the switch, okay, this is when we go what I call disfluxing. Okay, if we think about current first of all, opening the switch forces the current to rapidly drop from its initial value to 0. Now, when you close the switch, the rate of the increase is limited by the inductor. Okay, the inductor generates a back EMF which slows the increase. Okay, and that can take the increase quite a long time. But when you open the switch is dominating that behavior. You're forcing the current to drop rapidly. Okay, so we're using some terminology about rapid or fast decrease, or it's collapsing. Okay, so it changes very quickly. Going from its initial value of Vs over R, which is just Ohm's law, because the inductor, assuming an ideal inductor, would not really have any effect in the circuit, and it drops very quickly to 0. Okay, and if we look at the resistor voltage, using Ohm's law, we know the current's decreasing, we know R is constant. The resistor voltage must also be decreasing at the same rate. So it start at the supply voltage and drop away really fast. The inductor voltage does something very interesting. If we apply Faraday's law, we know that the inductance and the change in current are both constant. It's going from its maximum value to 0. But we've got a very small delta T. That means we're going to get a very large back EMF induced, which is actually going to vastly exceed the supply voltage. Okay, now that may seem a little bit contradictory based on something I said a little bit earlier. Okay, where did all that excess voltage come from, and where does it go to? What's going on with Kirchhoff's voltage rule? Because if we looked at Kirchhoff's voltage rule from before, we've got a supply voltage, we've got an inductor, we've got a resistor. The voltage across the supply must equal the inductor and the resistor. But here we've got an inductor voltage that's going much larger, okay? Because before, the maximum value that the inductor voltage could be was the supply, which was true when you close the switch, but that is not true when you open a switch, because the directions of things have changed. Kirchhoff's voltage rule still does apply, but it looks different now, okay? The important thing is that the back EMF, when you close the switch, was opposing the supply voltage, okay? So it was kind of, if you think of the supply voltage as a positive, the inductor and the resistor were both negatives, they're both drops in voltage. But now, because the current is decreasing, the inductor is inducing a voltage in the same direction as the supply voltage. It is now working with the supply voltage. So that is not limited to it anymore, okay? Which means if you write Kirchhoff's voltage rule, we've now got Vs plus VL on one side, and we've got the things using the voltage on the other side. So Vs and VL in the same direction. On the other side, we've got VR, but that's not actually all of it, because there's actually another component in here, the switch. Most of the voltage is actually dissipated across the open switch, because the switch now has much more resistance. An open switch has a very high resistance, much more than any resistor that you would have in the circuit. And that actually causes it to arc between the contacts. So you've got Vs and VL acting together to produce a very large voltage, and that is dissipated across the resistance, but mostly across the switch. But that only happens for a very short time, okay? If we think about it in terms of the time constant, we've got a constant inductance, but our resistance is now very large because of the switch. The resistance of an open switch is very large. If you've got a number divided by a very large number, you're going to get a very small number, which means we get a very small time constant. Okay, so that's basically my sort of summary of like inductor behavior in DC circuits. In terms of exam questions, you're most likely to get calculation questions based on when you close the switch and time constants and things like that. And opening switches would more likely to be a question about explaining why you get such incredibly large voltages, and that's to do with the rapidly changing current. So you get a very rapid change in flux, so you get a very high induced voltage. You also, just on a safety point, need to be very careful if you're switching off a circuit that has an inductor in it, because those large voltages, you can get a shock from them. Cool. Thanks very much.